I want to extend a very special thank you to my latest Patreon follower, Chiff1, for a very generous contribution to this channel. Thank you so much. Without you, this channel would not be possible. Please remember to like the video and subscribe and hit the notifications bell and comment. Thank you. Hi everyone, we are moving on to step 4, which is extending phi q to the reals. And this is going to be by far the most difficult proof that we will do so far. It's a whole just onslaught of new symbols and ways of thinking about things that we've never had to do before. So the most we can do is, one of the things that I want to do with these videos, something that I've talked about many times, but something that always kills you when you're reading a math book is the author skips steps, and they don't make it explicit how they're getting from one spot to another. And in fact, at least once in Rudin's book, we found a spot where he wasn't even right. He made this big assumption that he wasn't even right when he said that in proving the Dedekind cuts that multiplication could be proved the same way that addition can. It can't. Because he made that leap, he was wrong. So I think that it dramatically just slows down our understanding of proofs by skipping those steps and making the reader figure out those leaps on their own. That doesn't make what I'm going to do here easier, but at least following step by step will get through it and not leaving anything out. So for now, we're extending q to the reals, and the integers and the rationals were very similar, but this is now a whole new thing. It's going to require new techniques and some other things, like I said. On the other hand, the interesting thing is that now we don't actually need to construct the reals the way we constructed the naturals, the integers, and the rationals, because now we're talking about the entire set. We already have the two sets, x and y, that are sets that have that are ordered fields with the least upper bound property. In other words, real numbers. We already have two sets of real numbers. We don't need to embed the reals into these, we're just using these. But now, using phi q, we're going to extend phi q to create an isomorphism that maps every number in x to a number in y. So how are we going to do that? First, we're going to have to figure out a way to look at these numbers in x and y. So if we take an element of x, then we're going to define dr to be the set of all rationals q, element of qx, such that q is less than r. Okay, so in other words, this is just basically a Dedekind cut. For whatever the number is, it's the set of all rationals to the left of that number, to the that are less than that number. Because this proof, I'm going to go very slow, and it's difficult. I'm going to have to split this step up into 2 videos, I think. So for this video, we're going to prove that our isomorphism is a bijection, and then in the next video, we'll do addition and multiplication. So with this set, if we let k be a positive integer greater than r, then k has to be an upper bound of dr, right? Because if dr is everything less than r, if k is bigger than that, then k has to be an upper bound of dr. So we're going to use this number. If you remember when we were looking at the Dedekind cuts, or when we're looking at the least upper bound property generally, for a set to have a least upper bound, first you have to show that it's bounded. And then if it has a bound and the set has the least upper bound property, then it will have a least upper bound too. So we know that, so we're just going to pick k as an integer upper bound of dr. So now we're going to look at the set, consider the set phi q of dr. So this notation is a little bit weird because this is not an element of x. We're talking about an entire set that's inside of x. So when we say phi of this set, what we mean is basically take every element of the set and apply phi to it. So that what we end up with is a set in Y that contains every element that corresponds to the elements of dr. Okay, so this is actually a set, and it's a set in Y. So it's a subset of Q and Y, which is a subset of Y. So QDR means the set of all elements, phi Q of Q, where Q is less than R, Q is an element of the rationals in X, and R is an element of X, okay? So what that means is that the less than check is done in X. Then we send all of those elements to Y. So the issue here is we know what dr looks like. It's the set of all rationals less than R. But what we don't know is what does this set in Y look like? We understand that it's the set of every Q sent to Y, but we don't know that it has the same properties as dr. So that's what we have to look at. So we know that, what happened to my pen? We know that phi Q is order preserving. We proved that last video. So phi Q of K must be an upper bound of phi Q of dr, right? Because dr was all the Q's less than R, and K was bigger than R. So that because phi Q is order preserving, or because phi Q is order preserving, then the phi K is going to have, phi Q of K is going to have to be larger than every phi Q of Q, because every Q is less than every K. So if phi Q of K is an upper bound of this set, then because Y has the least upper bound property, we know that phi Q of dr has a least upper bound. So we've made progress already. We know we have a set in Y, and we know that it has a least upper bound. So what we're going to do is we're going to set phi r of R as the least upper bound of phi Q of dr. In other words, so phi r of R is the supremum of phi Q of dr. Okay? So this is what I mean. It's already getting hard to wrap your head around, but we're going to keep going step by step. So we have a set in Y. It's a set of rational numbers. We know it's bounded. That means it has a least upper bound. And that is how we're defining phi of R. So R is an element of X. It's an arbitrary element of X. It doesn't even have to be rational. It could be anything. And what we're saying is that if you map that number, we're mapping it to the least upper bound of this set. So it's the set of all of the phi Q's that are where Q is less than R. There's a least upper bound. That's what we're setting phi R to. So once again, just like we've been doing, we're extending the previous isomorphism. So last time we defined phi of Q. Now we're using phi of Q to define what phi of R means. And we're using Dedekind cuts basically to do that in the least upper bound property. So with this definition, we need to show that phi of R is an isomorphism from X to Y. Okay. Proof. So again, first we have to prove it's a bijection, then we have to prove that it preserves addition and multiplication. Addition and multiplication we're going to do in the next video. This video, we're going to prove that it's a bijection, which means that it's a well-ordered function that is one-to-one and onto. Now, for naturals, integers, and the rationals, the one-to-one and onto was pretty obvious. And it was sort of intuitive. It was more intuitively obvious because you could see that if the x was, if one x is less than another, then the phi's are going to be less than each other too, that it preserves order, that it's 1 to 1 and on to. For reals, yet again, it's much less obvious, and dealing with the definition that we just made, it's going to take a lot more care to prove each of these things. Specifically, it's going to take more care to prove that phi r covers all of y. That there's, for every element of y, that some element in x sends, phi r sends to that element of y. So in order to do this, there's a whole lot of new stuff, new techniques and observations that we haven't used before, that they're not difficult, but it's new ways of getting to where we want to go. So I'm just going to go through them now, and then we'll use these in the rest of the proof. So some new techniques / observations. 1, to prove that A equals B, show both A is less than or equal to B and A is greater than or equal to B. So if you can show both of these things, then it can only be that A equals B. 2, if A is less than or equal to B, but A is not less than B, then A equals B. So if we start with this and we can show that A is in fact not less than B, then it must be that it's equal. And then something that we do that goes along with this is you assume that A is less than B, and then reach a contradiction from this. So then you're basically showing that A is not less than B, which means that A equals B. So frequently a way that we manage this is by assuming the opposite of this and then showing that there's a contradiction there. 4, so then again, using some information that we know, we can use transitivity of less than to create a contradiction. So here, so again, this we can also use this with this. So this is really a way to prove that A is not less than B. So again, you assume that it is, that A is less than B, then pick a number between them such that A is less than T is less than B. But then T is something that we know more about, and in fact we know that T is not less than B. So if T is not less than B, then A can't be less than B. Thus A is not less than B, so therefore if what we're trying to prove is this, then we know that A must equal B, okay? This is something we do a lot. You pick a number between the two where you can then prove that this part isn't true, so then the whole inequality must not be true. 5, similar to this one, you use transitivity to make create an impossible inequality, that A is less than A. So if you can figure out a way to make A less than A, then that can't be true. You've reached a contradiction or an impossibility. So again, then A must be B. So the way to do that is, so you assume that A is less than B, but you know that B is less than C and that C is less than A. But that means from the transitivity of inequality that A is less than A. That can't be true, so this part must not be true. So there you prove that A is less than B, or A is not less than B, so A equals B. So that's another thing that we'll be using sometimes. So in all of these, what you're doing is you're finding something that you know more about in order to say, but if this is true, but we already know that this is true, but then that would mean that this is true, which is impossible, so this must be wrong, okay? It's just like always assuming the opposite. So one more thing is that if A is less than or equal to B and we want to show that A is strictly less than B, another way to do that is you basically pry these two apart, because right now they might be equal or they might be A less than B. So what you basically do is you pry them apart by inserting things in that are strictly less than. So if we can show that A is less than or equal to some other number, which is strictly less than another number, if we know some number that is less than or equal to P, to A, and then we know that that number is strictly less than another number, which we know is less than or equal to B, then what we've shown here by transitivity, we've shown that if A is less than or equal to P, is strictly less than Q, which is less than or equal to B, then A has to be strictly less than B. So we showed that A is less than B. So that's that's one method that we'll have for proving that A is less than B. Okay, now these last two are not techniques. They're actually just observations that we've never used before, but have always been sitting there for us if we needed them. So since phi is 1-to-1 and onto, its inverse is also an isomorphism. So this isn't saying anything that we don't already know, because like for instance, when we were doing the rationals, we had that, so we need to define an A over B such that phi of A over B equals C over D. So if this is true, then obviously you can just name a function the other way. Just name a function phi, the inverse of phi of CD, that gives us the A equals B, right? That's all we're doing here, that if phi is 1-to-1 and onto, then it has an inverse, which is also an isomorphism from y to x in the other direction. Now, so far we haven't needed this notation because it's just as easy to just say there exists some x such that phi x equals y. The reason we need this now is because we're also going to be talking about our sets, our Dedekind cuts in y and how they relate back to x. We're going to have to be able to use those sets and go both directions. So we're going to have to define a set, which I call D star in R, that's a subset of y, and then we need a way to go back from y to x and talk about the set that corresponds to a similar set in y. So if this is the set in y, then we'll talk about the inverse of phi which would be a subset of x. Okay, so again, I know this here, again, the notation is getting very confusing. We'll just have to go slow and it'll hopefully get more comfortable. So, okay, and there's one more. I ran out of room, so I have one more to show us. One more observation. And that is an interesting one, that order preserving implies 1, 2, 1. This is interesting because the way we've been proving 1-to-1, 1-to-1 is if f of x equals f of y, that implies that x equals y. So we've been looking at it from an equality. But there's another way that you can do it, which is actually looking at the relation between them. Because if the function is 1-to-1, that means that it's monotonic, right? It's always increasing. So that means that if you have an x and a y here, then f of x and f of y are going to have the same relationship. So to prove it, if x does not equal y, then either x is less than y or y is less than x, right? So then because it's order preserving and it must be strictly increasing, that means that either f of x is less than f of y or f of y is less than f of x. That means that f of x does not equal f of y. So what we did here is we're showing that if x does not equal y, so this is using order preserving, that if x is less than y, then f of x is less than f of y. But if this is true of the function, then we showed that x not equal y implies that f of x does not equal f of y. This is the contrapositive of what we normally do. So what we normally say is that f of x equals f of y implies that x equals y, right? And so the contrapositive of a statement like this is that if the conclusion is not true, then the premise is not true. So if x does not equal y, then f of x does not equal f of y. So we're basically just proving the same thing, but doing it in the opposite way. So it's interesting. So if we can show that a function is order preserving, that implies that it's 1-to-1. You can prove 1-to-1 without looking at the order preserving, but if you start with the order preserving, it shows that it's 1-to-1. Now, those are just some techniques and observations that we'll be using. In addition to that, I could maybe call these also observations, but I called these some useful properties that we'll be using all the time too. So P1 is that rationals are dense in the reals. P2 is that R is the least upper bound of dr. And P3 is that the phi q of R equals phi R of R when R is an element of the rationals. So that rationals are dense in reals is something that we proved when we were looking at real numbers. It just means that between any two real numbers, there's a rational number. That R is the least upper bound of dr is kind of obvious, but we need to show it real quick, that since this is the set of all rationals less than R, that means that R is the least upper bound. And this is very important. So basically we're starting here with nailing down the phi for the reals a little bit by showing that at least as far as the rationals are concerned, whatever phi q of R is, phi R of R is the same if R is a rational. This is the basic point. We're basically showing that for phi R, at least as far as rationals are concerned, we're nailing them all down. And then with that in mind, we're going to be able to then fill in all the irrationals in between. Okay, so the proofs, let me go to the next page. So P1 we've just already proven that the rationals are dense in the reals. We proved that when we were doing the videos on real numbers. P2, that R is the least upper bound of dr. So assume that R is not the least upper bound. That means that there's some other element less than R that is also an upper bound of dr. Right? But because the rationals are dense in the reals, we can find I don't know what that letter that was. We can find a P in the rationals that's between, right? This is what density means, that for any two reals, there's a rational between them. But if that's the case, this rational is still less than R, which means it's in dr. That means that Z cannot be an upper bound of dr because we found an element of dr that's larger than Z. So R has to be the least one because anything less than that isn't going to be an upper bound. P3, so we need to show that phi R of R equals phi Q of R when R is an element of Q. In other words, phi of R sends rationals to rationals. So to show this, if R is rational and Q is an element of dr, okay, so R is any rational and then Q is an element of the set that's all Q's less than R, then phi Q of Q is going to be less than phi Q of R because phi Q is order preserving. We learned that last time. That means that phi Q of R is an upper bound of dr, right? So we at least know that phi Q of R is bigger than everything, but we know it's an upper bound, not necessarily the least upper bound. So we know that the least upper bound of dr is phi R, is the least upper bound of dr. That's by definition. That's our definition of this isomorphism, of this map. So this is the least upper bound of phi Q of dr. So we know that phi R of R is the least upper bound of this set in Y. But what's interesting is what we don't know yet is that even though R is a rational number, we don't know that this is a rational number. So that's what we're trying to show. So we have shown that this is an upper bound. So that means that we know now that phi R of R is less than or equal to phi Q of R. Because what we showed is that phi Q of R is an upper bound, phi R of R is the least upper bound, so we know that it's either less than or equal to. This isn't going to be less than, it's either less than or equal to. Now we have to show that in fact it's not less than, it's actually equal. Okay, so how do we do this? We use one of our techniques. We're trying to prove that phi r of r is not less than phi q of r, we're going to do that by assuming the opposite. So assume that phi r of r is strictly less than phi q of r. Then, because of the density of rationals, there exists a rational number t that's in X such that phi r of r is less than or equal to phi q of t is less than phi q of r. Oh, not strictly. This is just also less than. So we know that. So we're assuming that phi r of r is less than phi q of r. So that means that there's going to exist a t such that phi r of r is less than phi q of t is less than phi q of r. Now, how do we know that? We know that because what we're doing is picking a number. We know that if this is, we're assuming that this is less than this, right? So what we're actually doing is picking a number in y that's between these two. It can be rational because the rationals are dense in the reals. And then, because phi is 1 to 1 and onto, we know that there exists a t that will map to this number. So we're actually saying that there's a t such that q of t is between these two numbers. Okay, so this implies, because phi q is order preserving, this implies that t is less than r. That means that t is an element of dr. That means that phi of q of t is an element of the set, of the set in y, because this is the definition of y, that it's every t that is in dr, it's the phi of q of that in y. But what's the problem? If phi q of t is an element of phi q of dr, then it has to be less than the least upper bound of phi q of dr. That means that phi q of t is less than phi r of r, because this is the least upper bound of this set. But we started by assuming that phi r of r was less than phi r of t, or phi q of t. We just showed that phi q of t is actually less than phi r of r. That's a contradiction. That means that this assumption is wrong, and then if this is not less than this, it can only be equal to. So therefore, phi r of r equals phi q of r. So what that means is that at least as far as the rational numbers are concerned, if the r that we're using to make our set, if the r is rational, then phi of r is the same as phi of q. So we've extended phi of q to the real numbers at least as far, to the real map, at least as far as rational numbers go. Okay, that's a good start. I'm going to stop here. Next week we'll do well-defined, one-to-one, and onto, and then we'll do addition and multiplication. So come back next week. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.